Hello, my name is Jeff Diebold, and this presentation will discuss several recent R&D programs at advanced cooling technologies related to spacecraft thermal control. Several of my colleagues at ACT were involved in these programs, and a few of them will be speaking during this presentation. I'll begin with a discussion of a vapor venting thermal management system. Then Sai-Kiran Hota will discuss a system for cooling power electronics. Then Kuan-Lin will discuss a system for lunar ice extraction, and Ellis Seber will discuss a variable conductance cold plate. As part of a phase one NASA SBIR, ACT designed a thermal management system to maintain the temperature of a sample acquired during a sample return mission. This concept could be applied to Mars, lunar, or comet sample return missions, all of which have different temperature requirements depending on the particular sample and the scientific goals of the mission. The concept, illustrated here on the right, utilizes a working fluid to absorb the heat via the latent heat of vaporization. It's made up of several concentric chambers. The central chamber is the sample chamber. This is surrounded by the bladder chamber, where the working fluid is stored as a liquid in a flexible bladder that wraps around the system. The bladder is surrounded by a gas, which pressurizes the bladder and provides passive pumping. A valve can be opened to allow liquid to flow from the bladder into the next concentric chamber, known as the vapor jacket. In the vapor jacket, the working fluid is in a two-phase saturated state, with liquid being stored in a wick along the walls. As vapor enters the vapor, or rather as heat enters the vapor jacket, the working fluid is vaporized and the pressure and temperature within the vapor jacket increase. At a predetermined set point, a second valve can be opened, venting vapor from the vapor jacket and reducing the temperature. The vapor can then flow through the final chamber, known as the heat guarding chamber, to absorb additional thermal energy as sensible heating before the vapor finally vents to the environment. There are several advantages of this concept. It is lightweight. It has a continuously adjustable set point. The temperature control point can be selected, can be any value by selecting the correct working fluid and the temperature or pressure at which you vent vapor. There are minimal moving parts and minimal energy requirements for the system to operate. Here we see the phase one proof of concept design. We selected a temperature set point of 15 degrees C, and we used acetone as the working fluid. Now, this isn't necessarily representative of any sample return mission, but was selected to be below the ambient temperature to provide heat load from the ambient environment, and was just selected as our proof of concept design. The 3D CAD model here on the left shows the prototype. You can see the several concentric chambers color-coded here, as well as the plumbing involved. The blue liquid line, which allowed liquid to flow from the bladder to the vapor jacket, and the red vapor line, which allowed vapor to flow out of the vapor jacket into the heat guarding chamber and ultimately out of the system. The flow of liquid and vapor was controlled via solenoid valves, which were triggered based on temperature and pressure measurements. On the right, we see the prototype placed within a bell jar. This was done so that the system could vent the low vapor pressure of acetone into an environment that was at a lower pressure. Heat loads were provided by a constant heat load from the ambient being warmer than the set point temperature. And then we also added an additional heater to the prototype so that we could increase the heat load. Here we see some experimental results. Everything here is plotted against time. This whole experiment lasted roughly 5.5 hours. The sample chamber and vapor jacket temperature are indicated by the blue and green line respectively. The goal of the experiment was to maintain the sample chamber temperature at the target 15 degrees C throughout the entire experiment. The environmental temperature, indicated by the yellow line here, we can see was roughly 9 to 10 degrees warmer than the sample chamber. So this provided a constant heat load from the sample or from the environment to the prototype. The purple line here indicates the vapor pressure within the vapor jacket. We can see fluctuations in that pressure occurring due to opening of the vapor venting valve as well as the liquid charging valve. The brown line here indicates the estimated mass of fluid within the bladder. This was based on knowing the initial mass of fluid, knowing how many times the valve opened, and knowing how much liquid exited the bladder every time that valve was open. So based on that, we could use this estimated mass and the latent heat of vaporization of acetone to estimate an average heat load of about 3.8 watts during the first approximately 11,000 seconds of this experiment. At roughly 11,000 seconds, the external heater was turned on, and the outer wall temperature of the prototype, indicated by this red line, was increased by about 10 degrees. So during this time, we can see a few changes. First, an increase in frequency of the fluctuations in the vapor pressure due to the increased frequency at which the valves had to open to dissipate the higher heat load. We can also see temperature spikes in the vapor jacket. This was due to slightly warmer liquid from the bladder entering the vapor jacket. And then we can see a change in slope of the estimated mass, so indicating an increased heat load. So during this period of time, the average heat load was estimated to be about 8.4 watts. We can see a very slight increased temperature of the sample chamber by only about 1 degree, but ultimately this demonstrates the ability of this concept to maintain a nearly steady sample chamber temperature despite a changing thermal environment. Here we see a conceptual full-scale design for a vapor venting thermal management system designed for a cryogenic comet sample return. It contains all the key features, including the flexible flexible bladder, space for non-condensable gas to pressurize that bladder, the vapor jacket, heat guarding chamber, and even a removable lid with flexible lines to allow the vapor jacket to extend into the lid. A literature review indicated that in this temperature range, the highest latent heats of fusion for solid to liquid PCM materials was only about 75 kilojoules per kilogram. A few of the working fluids that could be used in a vapor venting system have latent heats of vaporization ranging from 200 to almost 500 kilojoules per kilogram. And then finally, a detailed mass comparison.
Hello everyone, this is Sai-Kiran Hota. I'll be presenting the advanced two-phase cooling system for modular power electronics developed under NASA SBR Phase 1 program. Jeffrey Didion was the program manager. The objective of this program was to develop advanced cooling system capable of handling high heat flux emanating from high power density electronics. We developed two-phase based heat spreaders for cooling a 3U card. One is the high K plate, which is embedded copper water heat pipes in an aluminum plate. The other is a pulsating heat pipe with propylene as the working fluid. We did performance testing of the cooling system with these two heat spreaders and compared it to the baseline case being aluminum plate as the heat spreader. In the performance testing, we used ice lock as the card retainer in place of quartz wedge lock. In this slide, I'll be introducing the pulsating heat pipe that was developed in this program. Now, the working fluid in the capillary channels redistributes itself as liquid slug and vapor plug. So in the evaporator, as heat is added, the saturated working fluid vaporizes and the local vapor pressure increases. Simultaneously in the condenser, the heat is rejected and the local vapor pressure decreases. So this combined effect of pressure difference between the evaporator and the condenser induces pulsation in the working fluid. So to observe the pulsation in a PHP, we did a small IR camera testing in a plate with two independent channels. On one side, we charged it with acetone, so that served as the PHP. The other side was empty, and so it was only a conduction card. So as you can see in the video, on the PHP side, you see pulsation from the center to the edge. The other side, it's just plain conduction. So in this particular testing, we saw up to 4 times improvement in thermal conductivity. Before the performance testing, we did trade study of the high K plate and PHP heat spreaders to determine the heat transfer operating limits and also to predict the performance via the FE analysis. Now for both high K plate and PHP, the limits, the heat transfer limit we determined was more than 100 watts up to 44 degrees C operating temperature. In the case of the high K plate, if you look at the heat pipe layout, in the evaporator, which is near the center, and the condenser, which is around the edges on the same plane, the delta T is actually lower, but along the stepped plane, the heat transfer is just by the base plate conduction, so the delta T is actually higher. In the case of PHP, the unique feature here is shape matching, which means we have the two-phase capillary channels extending along the stepped plane. So the delta T along the stepped plane is actually lower than the case of the high K plate. Before the performance testing of the new heat spreaders that we developed, we established the baseline with aluminum plate as the heat spreader. The center temperature is basically closer to the source, and the coolant is the sink temperature. In the baseline case, without exceeding the maximum safe to touch temperature of 44 C, we can transport up to 21 watts of heat. The overall system thermal resistance was a little over 2 degrees C per watt in this case. In the case of high K plate based cooling system, up to 36 watts of heat can be applied. And the total system thermal resistance was around 1 degree C per watt. So this is basically more than 50% reduction in overall system thermal resistance compared to the baseline. In the PHP based cooling system case, a little over 38 watts of heat can be transported. The overall system thermal resistance was also around 1 degree C per watt, which means more than 50% reduction in overall system thermal resistance. Here you see the instantaneous temperature profile of the cooling system from the center of the heat spreader to the coolant, which is near the sink. We actually see a good isothermality in the case of high K plate between the center and the edge. But along the step plane from the edge to the rail, the delta T in the case of PHP is actually lower than the high K plate. Like I explained, we actually have good shape matching, so the capillary channels extend into the step edge. So we have lower delta T in the case of PHP. Overall, the thermal performance of PHP is better than the high K plate, but both are significantly better than the aluminum plate. So to summarize, in this program, we developed high K plate and PHP based heat spreaders and did performance testing in the cooling system and compared it against aluminum baseline, where we saw more than 50% reduction in the overall system thermal resistance. We also did testing in the vertical and horizontal orientations with the high K plate and PHP plate based cooling system, where we did not see much change in thermal performance. The unique advantage with the PHP is shape matching, where we have the two-phase channels extending onto the strut plane in this particular, which was developed in this program. Another advantage with the PHP is mass savings as opposed to the high K plate.
Hello, my name is Kuan-Lin. I'm going to talk about waste heat-based thermal core developed under the NASA Phase 2 SBR program. In this program, ACT, in collaboration with Honeybee Robotics, is developing the thermal management system for lunar ice miner for future lunar ISRU applications. The thermal management system's schematic is shown in the lower right corner. In this systems, we use the waste heat of MMRTG to extract ice from the icy regolith. And the systems use a pump fluid loop to deliver heat from the cold end of the MMRTG to the thermal core with embedded mini channels. And the vapor, sublimated ice vapor, will travel through the rotor unions and eventually reach a cold trap tank with a heat pipe radiator for ice collection. Today's presentation will mainly focusing on the development of thermal core. This slide summarizes the proof of concept thermal core developed under the Phase 1 program. The length of the core is 6 inches with mini channels embedded, as you can see in the X-ray image. The material is 316 stainless steel, and it was made by additive manufacturing. To test the functionality of the thermal core, we test the thermal core onto a benchtop experimental system shown on the right-hand side. In this test, we mix the water and LHS regolith simulants and chill the mixture to minus 50 degrees C. And then we circulate 50 degrees C water through the thermal core for ice extraction. We successfully extract 1.5 gram of the water, which is about 44% of the total extractable water in the ice soil surrogate mixture. One of the objectives in Phase 2 is to optimize the thermal core design so that we can have a maximized ice extraction rate and reduce the pumping power for heat transfer fluid to go through the mini channels. The design parameters include thermal core geometry, length, and diameter. Also, the mini channels distribution as well as the size. Figure on the right shows the current design for the mini channels. We have 4 parallel spiral mini channels for hot fluid to travel from the top to the bottom. And we also have 4 straight annular flow channels for cold fluid travel back to the top. In addition to thermal and fluid modeling, we'll also do a structural analysis to make sure the design will be able to sustain after drilling into the IC regulus. This slide shows the modeling tool we developed for thermal core optimization. The model was built in the ANSYS fluid environment as a 2D transient model. The heat transfer between the heat transfer fluid and the solid wall material is described by conjugate heat transfer model. And the heat and mass transfer during the extraction process was described using the UDF because the material, the IC regulus thermophysical property depends heavily on temperature, pressure, and ice concentration. Here is some calculation results based on this model. Temperatures is showing on the left. Ice mass fraction is showing on the right. Change during the expression process. In this case, we circulate 50 degrees C water through the thermal core, and we are able to complete sublimation within 1500 seconds. We also use this model to investigate the effect of some design parameter, such as the back pressure. The back pressure here actually means the cold trap tank pressure. So when the back pressure is low, the extraction rate increase. Currently, we are developing an experimental system to validate the numerical model. The figure shows here is the 3D printed subscale prototype with mini channels embedded in the wall material. And the experiment system schematic is shown on the left-hand side. It has a regulus, IC regulus, housing, cold trap tank, and vacuum systems, and a lot of instrumentations. A figure on the right shows the IR testing results for the thermal core. When we circulate hot water through the core, we can see the temperature increases and also temperature distribution throughout the thermal core. This is still ongoing phase 2 effort, and this is my perspective.
Hi, my name is Ellis Seber, and today I'm going to talk a little bit about the variable conductance cold plate being developed here at ACT under a Phase 2 SBIR program funded by NASA. The premise of this program is that electronics instrumentation, such as those used in low-orbit satellites for monitoring environmental change, can be very sensitive to temperature change. Such instrumentation should be maintained at a constant temperature despite changing conditions. Therefore, the purpose of this project was to create a cold plate that can maintain isothermality of the heat collection surface, where these electronics are mounted, both spatially and temporally. As cooling conditions change, such as on a radiator or on a satellite, or as the heat load of electronics change, the VCCP, variable conductance cold plate, is able to prevent rapid temperature deviation of the mounted devices. On the bottom right, we can see a concept image of the variable conductance cold plate. Please note that the features are exaggerated just to make it easier to see. Starting at the top, we see the heat collection surface where this electronics would be mounted and generating heat. Beneath that is a vapor chamber, which consists of a large vapor space. This vapor chamber helps spread out the heat, and due to the nature of the two-phase working fluid held at saturation within the chamber, it provides a highly isothermal surface. Beneath the vapor chamber are variable conductance heat pipes, which not only transport the heat to a two-phase heat exchanger, but also provide the temporal isothermality in this system. A non-condensable gas takes up residence within the heat pipe condenser, and as the sink temperatures or as the heat loads change, the gas expands or retracts, covering or revealing portions of the heat pipe condenser. This is what gives the heat pipe its variable conductance. On the bottom left, you can see some of our goal parameters for this program. One item that I want to highlight is that our heat collection surface will ultimately have an area of half of a square meter, which is quite large for a vapor chamber. During the phase 1 of this program, we developed an analytical model of the cold plate to help in the design of it. To start, input parameters such as heat load, basic geometries of the system, etc. are defined. The desired outputs of this model are the temperatures of the heat collection surface and temperatures throughout the cold plate. So starting at the condenser portion of the VCHP, a thermal resistance network was made to determine the temperature of the vapor within the heat pipe. The resistances in this network can be calculated using the predetermined geometries and known correlations. Using these calculated resistances, the initial temperature of the coolant, and the power load each heat pipe is expected to dissipate, we could derive a vapor temperature for inside of the constant conductance heat pipe. A little more work needed to be done to determine the vapor temperature for using a variable conductance heat pipe. To determine this, a relationship between the non-condensable gas and the working fluid vapor needed to be established. The ideal gas law provides a good approximation for the behavior of our selected non-condensable gas. Whether the vapor temperature is at a maximum or at a lower arbitrary value, the number of moles must be the same for all cases between the reservoir and the condenser. So using these considerations, we are able to develop a function that is reliant on the vapor temperature, the sink temperature, and the heat load, which this function can then be formulated to determine the vapor temperature. With this more accurate vapor temperature, we could then use another thermal resistance network to model the heat transfer between the vapor of the heat pipe and the heat collection surface of the cold plate. With this completed model, we were able to vary different geometries of the system to find the optimal dimensions. This model works very well for optimizing the heat pipes, but optimizing the vapor chamber required a different approach. The limiting factor in vapor chamber performance is the capillary pumping power of the wicks, as they bring liquid back up to the heat collection surface. Fluid flow in the wicks could then be modeled using the thermal flow analogy for porous media, which states that since the governing equations for thermal conduction and porous media flow are mathematically equivalent, they can be used interchangeably so long as the coefficients are properly adjusted. Therefore, we could use a finite element analysis simulation for thermal conduction to model flow through the porous wicks. Using the analytical model and the FEA thermal flow analogy, we designed a subscale prototype to use for testing. In phase 1, this prototype was fabricated out of aluminum alloy using direct metal laser sintering. The phase 1 model consisted of 3 VCHPs, and the cold plate was charged with acetone in the vapor chamber and acetone and argon in the VCHPs. A simple, single-phase pump loop was constructed for testing the variable conductance cold plate, and our test consisted of rapidly changing the coolant temperature and recording how the surface temperature of the VCCP changed. We supplied a constant heat load of 38 watts to the heat collection surface, which was accomplished using 15 1-inch squared heaters across the 55-inch square surface. And you can see in this image that prototype for the phase 1. Looking at the graph to the right, we can see that despite rapid temperature changes in the coolant, the heat collection surface was very slow to react. I'd also like to comment that the spatial isothermality was held to be less than 2 degrees difference across the surface of the cold plate. During the ongoing Phase 2 program, ACT is currently in the process of fabricating another subscale prototype. This time we're using ammonia as the working fluid, as it is preferable for space applications. This model was designed using the same analytical model as described previously. The CAD image on screen shows what this model would look like if we chose to additively manufacture the plate in one go, with the adiabatic section of the heat pipes wrapping around to form a compact cold plate. Instead, we chose to fabricate the vapor chamber and the two-phase heat exchanger separately, as we'll see in the next image. I do want to note that on the interior of the vapor chamber, the heat pipes were fully embedded within the vapor space. This was done to limit the thermal resistance. And now, as you can see here, this is the fabricated Phase 2 subscale VCCP. While some work is still being done to complete the fabrication, such as we still need to charge the heat pipes, this cold plate is really just about ready for testing. And you can see on the right-hand side here, this is our test bed, which we've placed inside of a fume hood for safety since we are working with ammonia. Moving forward, we will be fabricating a full-scale model of the cold plate, which will boast a heat collection surface of half of a square meter. ACT would now like to acknowledge those that have supported the programs discussed here today. Each of these programs were funded under a NASA SBIR program, and we would like to thank our respective technical monitors, Brian Palazewski, Nina Noorani, and Jeffrey Didion, as well as our technicians Eugene Swigart, Larry Waltman, Justin Boyer, and Ariana McGee. We at Advanced Cooling Technologies would like to thank you for your time. If you have any questions regarding the work discussed here today, or if you would like to learn more, please reach out to us. Thank you.